Algorithms Design and Analysis, Introduction, Performance Analysis, and Asymptotic Notations. Welcome to this lesson on Algorithms Design and Analysis. In this lecture, we will cover three fundamental topics that form the foundation of algorithmic thinking in computer science. First, we will understand what an algorithm is and learn its essential characteristics. Next, we will study performance analysis, including time complexity and space complexity. Finally, we will explore asymptotic notations such as big O, omega, theta, and little o, which are mathematical tools used to analyze the efficiency of algorithms. Let us begin with the concept of an algorithm. The word algorithm has an interesting historical origin. It is derived from the name of the 9th century Persian mathematician and astronomer Abu Ja'far Muhammad ibn Musa al-Khwarizmi. When his works were translated into Latin, his name became algorithmi, and over time this evolved into the modern word algorithm. In computer science, an algorithm can be defined as a finite sequence of clear and unambiguous instructions that are executed in a specific order to solve a problem. The algorithm accepts some input, performs a series of logical steps, and produces the desired output within a finite amount of time. You can think of an algorithm as a recipe. Just as a cooking recipe provides step-by-step instructions to prepare a dish, an algorithm provides step-by-step instructions to solve a computational problem. The important point is that an algorithm describes the logic of the solution and is independent of any programming language. Every algorithm follows a simple flow. First, it receives input values. Then, it processes those values through a sequence of logical operations. Finally, it produces one or more outputs. This input-process-output model forms the basis of all computational systems. Now, let us understand the difference between an algorithm and a program. Many people use these terms interchangeably, but technically, they are different. An algorithm is a conceptual solution to a problem. It represents the logic and design of the solution. A program, on the other hand, is the implementation of that algorithm in a specific programming language, such as C, C++, Java, or Python. An algorithm is language independent, whereas a program is language dependent. An algorithm cannot be executed directly by a computer because it is only a description of the steps. A program can be executed because it is written in a language that the computer can understand after compilation or interpretation. Another important difference involves termination. An algorithm must always terminate after a finite number of steps. However, a program does not necessarily have to terminate. For example, operating systems, database servers, and web servers are programs designed to run continuously for very long periods. If a process satisfies all characteristics of an algorithm except termination, it is often called a computational procedure rather than an algorithm. Now, let us discuss the fundamental characteristics that every algorithm must satisfy. The first characteristic is input. An algorithm may have 0 or more inputs. These inputs are the values supplied from outside the algorithm. Some algorithms require user input, while others may generate data internally. The second characteristic is output. Every algorithm must produce at least one output. The output represents the solution to the problem that the algorithm was designed to solve. The third characteristic is definiteness, also known as unambiguity. Every step in the algorithm must be clearly defined. There should be no confusion about what action must be performed at any stage. If an instruction can be interpreted in multiple ways, then it is not suitable for an algorithm. The fourth characteristic is finiteness. An algorithm must always terminate after a finite number of steps. Regardless of the input values provided, the execution must eventually stop and produce a result. The fifth characteristic is effectiveness. Every instruction in the algorithm must be simple enough to be performed accurately within a finite amount of time. In principle, Each step should be executable by a person using basic tools such as pencil and paper. These 5 characteristics: input, output, definiteness, finiteness, and effectiveness, are considered the fundamental requirements of a valid algorithm. Now that we understand what an algorithm is, let us move on to performance analysis. Performance analysis is the process of evaluating how efficiently an algorithm uses computational resources. The 2 most important resources are time and memory. By analyzing these resources, we can compare different algorithms and determine which one is more efficient. Performance analysis is generally divided into 2 categories. The first category is called a priori analysis. A priori analysis is performed before the algorithm is implemented. It is a theoretical analysis that studies how the running time and memory requirements grow as the input size increases. Since it is theoretical, it does not depend on the computer hardware, operating system, compiler, or programming language. Instead, it focuses on counting the number of fundamental operations performed by the algorithm. The second category is called a posteriori analysis. A posteriori analysis is performed after implementation. In this approach, the algorithm is coded, compiled, and executed on real systems. Actual execution time and memory consumption are measured using experimental testing because it depends on hardware and software environments. The results may vary from one system to another. Next, let us study space complexity. Space complexity refers to the total amount of memory required by an algorithm during its execution. It describes how memory usage changes as the input size grows. The total memory requirement of a program can be divided into 2 parts. The first part is called fixed space. Fixed space includes memory that remains constant regardless of the input size. This includes memory for instructions, constants, and fixed size variables. The second part is called variable space. Variable space depends on the size of the input. It includes memory used by dynamic data structures, recursion stacks, and other storage that grows during execution. Let us understand this through an example. Suppose we have an algorithm that calculates the sum of all elements in an array using a loop. The algorithm uses only a few variables, such as the array size, a loop counter, and an accumulator variable to store the sum. The number of variables remains constant, regardless of how large the array becomes. Since the memory requirement does not grow with the input size, the space complexity is constant. We denote this as big O of 1, or O of 1. Now consider a recursive version of the same problem. In the recursive approach, each function call creates a new activation record on the call stack. If the array contains n elements, then the recursion depth may also become n. As a result, the amount of stack memory grows linearly with the input size. Therefore, the space complexity of the recursive version is theta of n, which means linear space complexity. Let us now move to time complexity. Time complexity measures how the running time of an algorithm grows as the input size increases. Since actual execution time depends on hardware and software factors, we analyze algorithms by counting the number of fundamental operations they perform. This process is known as step count analysis. Consider the example of summing the elements of an array using a loop. The algorithm initializes a variable to 0, iterates through all n elements, adds each element to the total, and finally returns the result. The initialization step executes once. The loop condition is checked n plus 1 times. The addition operation executes n times. The return statement executes once. Adding all these counts together gives a total of 2n plus 3 operations. As the value of n becomes very large, the constant value 3 becomes insignificant compared to 2n. Therefore, the running time grows linearly with n. We express this as O of n. Now consider matrix addition. Suppose we add two matrices, each having m rows and n columns. To compute the result, we must visit every element of both matrices exactly once. This requires two nested loops. The outer loop runs m times, and the inner loop runs n times for each iteration of the outer loop. Therefore, the total number of operations is proportional to m multiplied by n. If the matrices are square matrices where m equals n, then the running time becomes proportional to n squared. Thus, the time complexity is O of n squared, which is called quadratic complexity. Now, let us move to one of the most important topics in algorithm analysis: asymptotic notations. Asymptotic notations help us describe how an algorithm behaves when the input size becomes extremely large. Instead of focusing on exact running times, asymptotic analysis focuses on growth rates. This approach allows us to compare algorithms objectively without worrying about machine speed, programming language, or compiler optimizations. The main idea is to ignore constant factors and lower order terms because they become insignificant for very large inputs. The first notation we will study is Big O notation. Big O notation provides an upper bound on the growth rate of a function. In simpler terms, it describes the maximum amount of work an algorithm may need to perform. When we say that a function f of n is O of g of n, we mean that beyond a certain point, f of n never grows faster than a constant multiple of g of n. Big O is commonly used to describe the worst-case performance of algorithms. For example, consider the expression 3n plus 2. As n becomes very large, the dominant term is 3n. The constant value 2 becomes negligible. We can show mathematically that 3n plus 2 is less than or equal to 5n for all values of n greater than or equal to 1. Therefore, 3n plus 2 belongs to O of n. Similarly, consider 10n squared plus 4n plus 2. For large values of n, the n squared term dominates the expression. The linear term and constant term become relatively insignificant. We can show that this expression is bounded above by 16n squared for all values of n greater than or equal to 1. Therefore, 10n squared plus 4n plus 2 belongs to O of n squared. Next, let us discuss omega notation. Omega notation provides a lower bound on the growth rate of a function. While Big O tells us the maximum growth rate, omega tells us the minimum growth rate. When we say that a function f of n is omega of g of n, we mean that beyond a certain point, f of n always grows at least as fast as a constant multiple of g of n. Omega is often associated with best-case performance analysis. For example, consider 3n plus 2. Since 3n plus 2 is always greater than or equal to 3n, we can conclude that 3n plus 2 belongs to omega of n. Now let us study theta notation. Theta notation provides a tight bound on the growth rate. A function belongs to theta of g of n if it is both O of g of n and omega of g of n. In other words, the function grows at exactly the same rate as g of n apart from constant factors. Consider the expression 3n plus 2 once again. We have already shown that it is O of n and also omega of n. Since both conditions are satisfied, we can conclude that 3n plus 2 belongs to theta of n. Theta notation is particularly useful because it provides the most precise asymptotic description of a function's growth. The final notation we will discuss is little o notation. Little o notation represents a strict upper bound. A function f of n belongs to little o of g of n if f of n grows much more slowly than g of n as n approaches infinity. One practical way to verify little o notation is by using limits. If the limit of f of n belies that of n approaches 0 as n approaches infinity, then f of n belongs to little o of g of n. For example, consider 3n plus 2 divided by n squared. As n becomes larger and larger, the ratio approaches 0. Therefore, 3n plus 2 belongs to little o of n squared. This means that linear growth becomes insignificant when compared to quadratic growth for very large input sizes. Before concluding, let us compare the common complexity classes in order of increasing growth rate. The most efficient category is constant time complexity, represented by O of 1. Next comes logarithmic complexity, represented by O of log n. After that comes linear complexity, represented by O of n. Then comes linear arithmic complexity, represented by O of n log n. This is followed by quadratic complexity, O of n squared. Then cubic complexity, O of n cubed. After cubic complexity comes exponential complexity, O of 2 to the power n. Finally, factorial complexity, O of n factorial, which grows extremely rapidly and becomes impractical even for moderate input sizes. As input sizes become very large, algorithms with lower growth rates are significantly more efficient than algorithms with higher growth rates. To summarize this lecture, we learned that an algorithm is a finite sequence of unambiguous steps used to solve a problem. We discussed the 5 essential characteristics of algorithms: input, output, definiteness, finiteness, and effectiveness. We studied performance analysis through time complexity and space complexity. Finally, we explored asymptotic notations including big O, omega, theta, and little o, which allow us to analyze and compare algorithm efficiency in a machine-independent manner. Understanding these concepts is crucial because they form the foundation for designing efficient algorithms and evaluating their performance in real-world applications. Thank you for listening, and in the next lesson, we will continue exploring more advanced topics in algorithm design and analysis.